So where I stopped last time was this embarrassment here we are, a course in nonlinear dynamics, and I'm going to spend a week or as long as it takes, at least a week, until it sinks in on matters linear. Now the justification is, it's not so bad as it sounds. When they teach you general relativity, they teach you about curved spaces, but they teach you the way you learn about curved spaces is that you're in a local proper Minkowski frame. So, when you're evolving in that particular setting, as far as you're concerned, the world is flat, and as far as we are concerned, the world is flat. It's not a bad approximation. It's actually a very good thing to start with, and then later you learn how to compute curvatures, etc. So you're not in a flat space. So it's totally legitimate. And the main thing I want to do, I'll do something that is computationally, as far as I can tell, not very useful. If you have to compute Jacobians for a Slare attractor for short orbits, you do it on MATLAB just as we did it last year. There's an equation that says there are 9 components of Jacobian, and you integrate them along with the trajectory. There's nothing to it. If you want to do something more ambitious, like compute for longer times or in higher dimensions, you talk to Sean Ding, who knows, who has thought about it for 4 months and knows how to do it. But it's not totally trivial. But there is a conceptual thing that I think is very important to understand about dynamics. And this is that, when we are given somebody's equations and take them as the word of Lord and integrate them, we live in some arbitrary coordinate frame, in this room. Whereas what I'll describe today all happens in the co-moving frame of the representative particle of the state. And in dynamics, there might be really a lot gained to understanding how to be in a co-moving frame rather than some external fixed frame, because the external frames are very fixed and very stupid. They know nothing about what's really going on. So, my origin could be there, but the goal is over there. The soccer game is happening very far away. And to understand what's really going on, you want to be in the co-moving frame. And stability is the simplest example of it. So I'll spend a little time. And as I said last time, I'll do it as my student, very gifted student who decided to become an actuary and decided to solve equation in one dimension as a compound interest. So it used to be that interest was compounded annually or monthly, and the way it was done is that the derivative was replaced by your wealth at 2 different instants, divided by the interval of time, which could be 1 year or 1 picosecond, depending what you're doing. And that's proportional to constant interest. And that's per unit time, so it's a rate. And you rewrite this as x n plus 1, you multiply by delta, put on this side, and that's 1 plus delta lambda xn. And now, 100 years from now, you know what your pension plan will give you if it's computed this way. It's going to be x100 will be or 101 will be this to delta t lambda to 100 of what you started with. And Euler used this as one way to define an exponential. So he wrote this solution as a limit of many time increments. He replaced the total time by the number of increments. That's delta n. And in the limit of infinitesimal time, this is one of the definitions of the exponential. This is the simplest linear equation that we know how to solve. Exponential growth and exponential decay depending on lambda is positive or negative. You could be also have taken out a loan and your wealth could be decreasing. And that works also for matrices. So if you take a matrix A, instead of just one rate of growth, matrix is your d by d rates. And if you go through the steps, this is one of the definitions of the exponentials. So the equation x d-dimensional vector multiplying ax has a solution xt e to the t to the a of x at time 0. And basic definition of function of a matrix is that if you can write a Taylor series and you stick every place instead of constant lambda, if you stick every place a matrix, that's one of the definitions of function of a matrix. So you'll have no hard time understanding what this exponential means. But I still prefer the way the actuary thinks. The way the actuary would write this solution would be to say that my vector, d-dimensional vector, so now we are in our setting x is now state space, which is d-dimensional, where d-dimensional can be anything from 1 to infinity depending on the problem. Actually, we would say I can approximate this exponential by a product, and the product is, I start with my initial state x0, any place in the state space, and I apply to it this thing with lambda replaced by a matrix. So it's 1 plus time divided by number of steps matrix. Until the last term, lots of terms like that, n of them, and the last term t over n over a. Now, that could be written as the term by itself to the end, but you have to think about problem you're trying to solve. And our general problem is that we start at x0, and then we go some time, we end up at xt. And the way that this is done is that every place along we are using the local vector field to integrate our equation. So for example, it might be slow here, small vector, big vector. So this is v at x at time t. So as we move around, our vector field in nonlinear problem is varying. It's not constant. And the matrix, stability matrix or matrix of velocity gradients was defined as the local shear. So it depends on the space. And we'll assume that we are in autonomous systems, so that law at given point of space is just given. It doesn't change in time. Time dependence for that. So the matrix of velocity gradients is by definition, how velocity moves me in direction I. This is the dimensional vector. If I make a variation in direction xj. So that means that A will vary with time as well. So now we have this was true for constant. But now we have also definition for variable A. And now what happens is, these are matrices, and in general matrices don't commute. So I'm not allowed to change their order. So this will now be product, my discretized product of n terms, x0. And the first time I will measure the shear around my initial point. We always record Professor Goldman, that's a part of. I already have him on previous talks, we have lectures, we have now. And then we do it at the next step, delta t x1, where x1 is defined to be the value where the representative point is at time t1, and tn is the initial point plus n times tm, n times if you're using equal time intervals. It's not necessary, but you want to do this. So these are little ticks on the trajectory. This is x1, x2, and they're just computational ticks. And this is xn, and this is xn plus 1. So then we have to evaluate the stability matrix at this point, and so on, until we end up at next to the last, a x to the n. And again, they have to be ordered because they're matrices. And what this means is that just like in, is there anybody here who hasn't seen Dr. Strangelove? Raise your hand. Jesus Christ. I'm sorry to evoke a false deity. No reason. Well, it's one of the requirements for the course that sooner or later you see this movie, this Peter Sellers. And what happens in the movie, it's a movie about the world that we still inhabit. It's about people with assured mutual destruction. At some point, something goes wrong. Peter Sellers used to work for Germans, but doesn't do it anymore. Has a scheme, but at some point, American general who is from Texas is riding a Minuteman missile over to Russia like this, and he's in a co-moving frame. So that's an example. So if you want to see things as they're happening, they're in a co-moving frame. And as things change, he cannot use the same rule for pressure, blah, 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 this and that. It has to be done along the way. So we can also write this to the linear order in the time. We can write each one of these terms as e to the delta t I and x and e to the delta t I. So to linear order these things agree, and if you want to, I can give you exercises to test such things, but any theoretical physicist or engineer or mathematician knows this. Plus order of delta t squared. So now if it makes you happy, and it apparently makes lots of people happy, you can now write an elegant formula. And you can say that x at time t is these are exponentials, so just multiply them. Then I see that I have sum over delta t's. When delta t is small, the sum is called an integral. So I can write this as e to the integral from 0 to t dt a x of t. So you can take a continuum limit. Now, this is totally illegal because they don't commute. So you can't just stick them into same exponential. If this is the same matrix, they'll be legal. But as they're different, when I multiply two matrices, two exponentials, there is something called Baker-Hauser formula, which hopefully I'll run into sooner or later, that says, yes, I can write this as a sum, but then I get a commutator term, etc. So honest thing would not be good. So instead of that, people say, aha, I put a letter here, and I call it time ordered. So if you were ever mystified by time ordering quantum mechanics, it's the same thing. Whenever you have a linear problem and your matrix is changing in time, in quantum mechanics, the linear problem is the state space is called Hilbert state. The initial state is a point in Hilbert space, so it's a complex vector rather than real. This is called Hamiltonian, and this is an I over h bar in it, but it's the same thing as the way you solve linear problems. So whenever you have a linear problem on a varying orbit trajectory like here, this is just a trajectory, it's a finite evolution, you have this situation. And in classical case, you can understand what it is. And I personally only understand it this way. I don't know what time ordering means other than moving and being sheared as I go along.
Should be x of 0?
X of 0, definitely, thanks. So that's what I didn't manage to do the last time. And Claire didn't see any of that in China. So what can people see in China that's, a video and kind of educational like this?
I don't know.
You don't know. Answer is longer. You think that there is an USB cable that Chinese are listening to. Okay. So one thing we learned from this form, which is totally obvious, is very important to us. And this is that the linearized flow forms a group, or if you're only going forward in time, semi-group. And how does that work? So if you look here and you go to this point, you go for time t prime, so you end up here at this point, x at t prime. You're free to compute Jacobian for this part of the trajectory. So just going around here, you use this formula, or this formula, to t prime. Now what you do next is you decide to continue. So the way you continue is you go for another period of time, let's call it t double prime, and t double prime, but you started at this point, so you start at point x t prime. And once you're done, you have Jacobian for t plus t double prime, which started at x0. In other words, you can always write Jacobian for the sum of two times. And notice this is a billion. The t's are just numbers. I can commute those things. But it doesn't matter, maybe. As a product of starting someplace, going for time t prime, but you have to start at the end of this trajectory, so you have to start at the end point. So linearized flow meaning the trajectory plus its neighborhood, linearized neighborhood, just neighbors for which I don't notice the higher order in terms, has a group property, forms a semi. Now in this class is just a group because usually we can go backward and forward. You can integrate our equations. We know where we came from. We know where we are going. But in more general settings, a semi-group meaning just for positive time. This is for t equals larger to 0. Now, because if you only seen quantum mechanics in your life so far, you say, what's the big deal? Everything is a group. Everything I've seen is a group. Why is this being emphasized? Well, if you try to do anything else, so for example, if you try to do something I won't cover in this course, but it's covered in the book Semi-Classical Quantum Mechanics, which is a WKB approximation to quantum mechanics. It turns out that and it's also a periodic orbit theory like this. So semi-classical QM, it's not a group. Now you could say, well, there's some approximation to quantum mechanics, your problem. Okay. If you want to look at the deterministic system, there's a little bit noise to it. So for example, every so often, Professor Goldman enters the room or walks by. That's noise. And it turns out it's not semi-classical, but it's very important, very physical. So if you have noise plus nonlinearity, then it doesn't work. It's not a semi-group. There are operators like this, but they don't compose nicely at all for linearized flow. So doesn't work here, doesn't work here. Now suppose that you are an erudite nonlinear dynamicist who trusts anything they read in literature, and you will notice that about every, 8 out of 10 papers in nonlinear dynamics compute something called Lyapunov exponent, which is an abomination. And the reason why it's abomination, first, it doesn't mean anything particular, but second, you cannot, let me explain. In this course, we want to predict quantities of this type. Something is happening, you stick a thermometer into your pot, you measure the temperature, and you have a physical prediction. Our theory predicts what you're supposed to. Now, Lyapunov is computers talking to computers. This is like if you were doing statistical mechanics and you wanted to know what 10 to the 23 things do. You very accurately compute something on your computer and you compare it to something I compute on my computer. If it makes you happy, good, but it's not very smart. So it doesn't work for Lyapunov exponents. And at this point, I should add a rule for graduate students. Don't trust anybody over 30, okay? Whatever my opinion I might have, you will have your opinion. So you might love Lyapunov exponents for some reason that I don't appreciate. Now, our dynamical systems appear in two versions, always. From physicists' point of view, it tends to be natural to think in continuous time because lots of problems that we are interested in are posed in continuous time. I should say there are many, many very good problems, like, I don't know, refreshing the Google vector, which are not done in continuous time, but they're perfectly good problems. So what happens when you have discrete time? Now, discrete time is not so fancy. The Jacobian is defined the same way. Jacobian is a derivative of a map, and discrete time is just a special map where what you call time is an integer, but Jacobian doesn't care about that parameter, it cares about variation in space. So Jacobian, Ij, a discrete time, let's call it n, is defined as my map starting at x0, going to n time steps forward. And how does it vary in direction I if I perturb initial condition in direction z? Or if you want to, you can write it as dx at time n. Well, okay, I can put it this way. For discrete time, we tend to not put it in bracket, but just a subscript. Yeah. So that's Jacobian. It's the same definition, continuous and discrete. But for discrete time, we can use a very famous rule. For discrete time, if you look at f of 0 is identity, nothing changes. F of 1 you iterated once, and we will use short abbreviation without 1 in here. So if I step one time in forward in time and a step again, so I start at my initial point, step once and step twice, and I take a partial derivative of this thing, then I can use a chain rule because this is a function of a function. So this by chain rule is derivative of fi, derivative with respect to xk, evaluated at x equals function of x0 jk. Then I'll take a derivative of the argument, which is function itself, which is df k dxj. But this one is evaluated at this argument at x equals x0 initial point. And I recognize this as one-step Jacobian in time. So this is Jacobian, one-step Jacobian evaluated with x1 is initial point and one-step Jacobian as x0 initial point. So for discrete time, we have that j, if I iterate n times, it's obvious how it works. Jn of x0 n plus 1 is j for the last step xn times j, jx n minus 1 tuk j of x 0. So did I make any errors?
And this is on the first definition of Jacobian.
This one?
No, on the right side. But like dIFN, which means that dFNI or n.
Yeah.
There's he corrected in the second one.
You mean it should be here?
Yeah. Denominator as well.
And yeah, and then it's a little confusing because there are two indices, but that's correct. And it's okay here.
Yeah. And in first denominator as well, dj x0, dx0j.
Just a second. This is ij. What did you tell me in the first?
Above that,
Here.
dx0.
Yeah. Thank you. Thank you, Burak, who pointed out. Now I've censored the class because is the thing still blue? You know what happened? I don't know whether anybody watches these videos on the web, but what happened when I told you about the school teacher who discovered that she can tell her students everything, the microphone got disgusted and turned itself off. So the rest of the lecture is without noise, other than the background noise. Okay, so that's the discrete time situation. And now there is one particular version of discrete time we care about, which is if you're in a Poincaré section, because this is how we connected continuous time flows, which we dearly love and integrate, to discrete time flows, whose utility we still doubt, but at some point you will become believers. So what happens in this linear diversion when we do discrete Poincaré sections? So Poincaré map. So, we clearly should be able to compute what happens to any volume on Poincaré map, because remember what the setting was. We had a big space of all possible states, so state space. And, cleverly, it was filled with spaghetti, or vermicelli, very fine spaghetti, because every orbit was a fiber in the space, and it had the property of not crossing any other orbit. So this is a really complicated thing for nonlinear flow. And the claim was that you could design a hypersurface. This is d dimensions you could design a hypersurface, which is a section, Poincaré section, which is d minus 1 dimensional. So when you do your exercises for the layer, it's going to look totally obvious, 3, and then I cut it to a section, it's a plane, so I can see everything. In real life, the state space is, 60 or 100,000 dimensional, because that's kind of problems we solve today. 30 years ago we were very fascinated by parabola, but since that graduate student figured out on computer that parabola is really parabola, we don't do this so much. We publish the papers published on this still in infinitely many bad journals. But in research we don't do it. We have high dimensions now because we care about more difficult things now. And then you have to understand the Poincaré section is just 1 dimension less. So you have a million dimensions, you go to million minus 1 dimensions. So you would think, nothing is gained by this. It turns out it's a very intelligent step from million to million minus 1. An immense amount is gained by it. So you will have to do Poincaré sections if you, do anything in nonlinear dynamics other than just run computer forward in time. But if you try to understand things, that will be very important. So it's a manifold. And well, state space is kind of given to you up to coordinate reparameterization. You have to understand that nothing is kind of really given, because the same system can be done in Korea and in Germany. It's at the same time, but they're totally different coordinates. But it's the same system. It just somebody chose to do it differently. So the state space is not sacred either. It's only sacred by the fact that, if I have a state, the person in Japan has to have same state. So for example, Gibson, Halko, and I computed some solution of Navier-Stokes, whereas 2 people in Japan and 1 in England within same month computed the same solution. They had a prettier picture because they used coordinates that they liked, that editors of Fizerev letter like. So their solution showed up on the cover of Fizerev letter. Ours is just in some humble technical journal like Journal of Fluid Mechanics. And it took Gibson 3 weeks to prove it's the same solution. So, it's the same world, we're solving the same problems, but just having state space in your coordinates doesn't mean you understand it in everybody else's. But what you understand when things exist, if there's some invariant object in this space, it should exist in everyone. And that's why there will be such great emphasis on invariance in theory of nonlinear dynamics. This Poincaré section situation is much worse. There, nobody tells you what to do. You agonize, you look at the flow, and you finally decide, if I put some very complicated curved surface, I will catch stuff that I care about. So they're always local, they're almost never global. They're very personal, everybody gets a different one. Pictures in one are not helpful in another one, but for example, if I find the periodic orbit in my way of doing it, whatever Poincaré section you got, you have to find that orbit as well. So that's a topological object. Time cannot destroy it. Change of coordinates cannot destroy it. So while choosing these coordinates is this horrible thing that we always do in physics, we seem to need them to do calculations. We don't know how to do calculations without, or most of the time without being in coordinates. You have to understand all these things are coordinates, and you care about only invariant properties of the thing. Anyway, so now it's intuitively obvious that if I have a neighborhood, so I take some, in this Poincaré section, I take a neighborhood. So these are points. This is called x of n, the center, and plus dx of n. And hat means that anything that has a hat in it is in the section, which is embedded in the space, but it's in the section. It's quite obvious that as this thing progresses along, so this is a piece of a hyperplane that's being sent around, so it'll do something as you go around. And it's quite obvious that at some point it should come back. And it'll come back in a distorted way, etc. And what is not obvious, and it's also obvious that if you know how it does it in full space, we know how it does it in section. Because that's kind of obvious. I mean, you imagine there's a little, thing being sent around, and it pierces the section every place it's transverse. It's a small neighborhood, and we designed the sections so they're open in large neighborhoods. So, I'll get back. What's not obvious to me, at least, is that when I write a d minus d, when I write a Jacobian for the map, and I write it for the flow, it's not obvious to me that the multipliers of the flow will tell me what the multipliers of the map do, because map is chosen somewhat arbitrarily. So at least to me it's not obvious, so it's worth checking. And we checked in the books, a graduate student, former graduate student, and now, a former graduate student, Rytis Paškauskas, and I wrote some very complicated section. He's a very erudite man, raised in Russian tradition, comes from Lithuania. So if you can write it in a simple way, I'll be very grateful. I'll replace it in a book. But it doesn't lend itself to a lecture. It takes a little bit too much time, so I'll just tell you what the main idea is. So main idea is when you look in this small neighborhood, in the Poincaré section, and you start with your point xn. Well, actually, it doesn't matter. I started with xn someplace. Okay. But I went around on the center of the trajectory, came back. So, it has to be oriented, so it's oriented the way it is. It pierces out here. At this point, the velocity is evaluated at xn plus 1. And if you remember, xn plus 1 is my flow map in full state space starting at xn, but I evaluated at the moment tn, so tn is the return time. So, how long time I have to go to exactly land here. Okay, so that's something we compute, and that's how we compute the Poincaré return map. It's a function, it's this function, and we give it a name. It's a map. This is one-step map, and it depends on where I started, which maps tend to do in nonlinear dynamics. So that's all very fine, no problem. Now if I take a neighbor here, so there's a delta xn, there's a neighbor. The neighboring trajectory will take off, it'll do something. It won't be very different because, they're neighbors. Maybe I'll do something weird in 1,000 dimensions, and then we're projecting it only onto the blackboard here. And it'll go, maybe it'll pierce this thing and end up here. So this will be xn plus delta x just x. It ends up in a full state space, at time tn. Because the neighboring trajectories don't return back in the same instant, because the flow is shearing, velocity varies every place, so they don't come back. So to compute this, you have to compute this delta tau n to find the true intersection. This is really x n plus 1. This is just, where you ended up in a full world Tn times we're starting with x. This is in full space. This one is in the section. So then you have to scratch your head a little bit, and so there are a few pages of algebra, unless you give me a beautiful derivation. It should be very short. And the result is that when you do this, you find that J is a hat. So the one return time starting from Poincaré section and returning a Poincaré section is rank D minus 1 matrix. So it says morally, you compute it in D dimensions, but morally it's 1 dimension less, because I'm going from the section to the section, so I've gotten rid of 1 dimension. And more specifically, you find that J of x prime times this vector here we'll evaluate at this point, that's 0. So one of the eigenvalues of D plus a full matrix is 0, and that means I'm not allowed to perturb along the trajectory. Nothing is gained. I'm only allowed to perturb transversely to it. That's what it means. That's the idea of Poincaré section. And then locally, you can construct some coordinates in which, in local coordinates, this is really D minus 1, D minus 1 matrix. So, but in general, you're working in your own coordinates. So it's not obvious it's D minus 1. So it takes a little work to do this, but it's the same as what you expect. You reduce the flow to a map. And do me a favor, on the home page, I'm giving you a quiz. And it asks questions about this lecture. And the reason why you should do me a favor is to just see whether Burak will get an email if you complete the quiz. It's anonymous, so you don't have to. But this is just trying to figure out where you can imagine some grading system without reinventing the wheel. And this software that I'm using called Camtasia does that, offers quizzes.